All right, everybody. In this video, we're going to look at basic optimization. Optimization can typically be one of the more difficult things that students learn within calculus, just based on kind of the newness, if you will, of the types of problems and how wordy some of them can get. Like I said, this is a basic type of problem. It's one that most people start off learning when they start diving into optimization. So you'll see quite a few of these. They're going to be set up very similarly. Yeah, I'm hoping that you guys will feel comfortable after this video for optimization of basic strategies. But optimization, just as a reminder, it helps us find the largest and smallest values of a function, just depending upon where what we're looking at, whether it's a word problem like this or if it's the function itself within the graph. Constraints in mathematics, constraints allow us to, or give us like a binding set position within the problem that we can't surpass. We either can't go above it or we can't go below it. Constraints hold our problem to a specific spot. And with these optimization problems, you're going to need two functions. Specifically, these baseline problems, you need two functions, and you're going to need to rewrite one of them so that they are into one variable. And I'm going to show you what all that means in just a minute. So let's look at example one. You want to enclose a field next to a river. You have purchased 650 feet of fencing. Find the dimensions of the field that will enclose the largest rectangular area. Find the area. Now, they tell us here what type of shape they're wanting us to go for. Now, that's something that we always look for in optimization problems is, well, all right, what shape do we have? Is it two-dimensional, three-dimensional, what? So they're just asking us to find area, therefore it's two-dimensional, and they're asking us to basically construct. So here's our river. We are constructing a fence that's in the rectangular shape around this river. Now, we only need to build three sides because we are obviously enclosing that fourth side on the river, so we don't need four sides here. So we need to come up with the lengths of these sides. Well, why don't we call these shorter sides X, and we'll call the longer side Y. So now I have to think, what two functions really talk about rectangles, specifically area? Well, that's easy. We have an area function, and we know the area of a rectangle is simply length times width. Another one that we have is we have a specific amount of feet of fencing, and this is where we need to have a function that has our constraint in it. And an easy one for these types of problems when we're building like a fence or something like that, we have perimeter. And I know that perimeter equals, so we know that perimeter equals the sides, all the sides just added together. So we have 2x plus y. Well, in terms of our problem, we have 2x plus y equals 650. Okay. Now, for optimization problems, what I want to do is I want to be able to rewrite my problem, rewrite one of these functions so that I have one variable. I want to create a function that we can take the derivative of that doesn't just give us a constant or zero. So when I'm looking at this type of problem, I'm looking at this problem here, this function here. What I can do is I can rewrite this so that we have y equals 650 minus 2x. I can then take this and plug it into my area function, and that'll allow me to get one particular function with respect to x that I can take the derivative of. So we have, now we have area equals, we have area equals x times 650 minus 2x. Well, let's go ahead and simplify. I have area equals 650x minus 2x squared. So at this point, we can take the derivative of the area function with respect to x, and we get area prime equals 650 minus 4x. Now, going back to everything that we know about taking the derivative, I'm trying to find the maximum space, right? I'm trying to find the largest possible area for this particular problem. And so what do we do? How do we find those local min and maxes of a function? Well, we find the critical points from that first derivative. So by taking this first derivative and we set it equal to 0 and we solve for x, we can find our critical points. So when I divide both sides by 4, we wind up with x equal to 162.5. And so now what I can do is I can utilize this answer here to find the largest area and the values of those dimensions. So utilizing my functions from earlier, we can simply say, okay, well, plugging into the perimeter function here, or rather here, we can say y equals 650 minus 2 times 162.5. Well, that's 650 minus 325. So y equals 325. So in terms of our problem, we have 325 feet here. We have 162.5 feet here, and also 162.5 feet on this side. But now the problem wants us to find what the area would be for that largest area. Well, that's pretty simple. We utilize our area function here. So area equals 325 times 162.5. We wind up with an area of 52,812.5 square feet. And that is the basic optimization problem. Again, utilizing those two functions and finding where, or utilizing those two functions to get one of those functions in terms of one variable, and we take derivative with respect to what the problem is asking us for. So I hope this video helped. Thanks for checking it out. Be sure to check out the ones for more advanced optimization problems, and I'll see you next time.